Now that we've gone through nonlinear equations, we're going to see how we can utilize that to graph inequalities and to solve systems of inequalities instead. So the first thing we're going to do is get some practice with just graphing an inequality in general. Then we'll work in graphing both of these being true to get some region that will satisfy both of these. So let's start with the equation or the inequality 4y minus 3x is less than or equal to 5. So in this case, it's linear because the x variables and the y variable are both to the first power. So we're going to solve this inequality for y instead. So I've got 4y minus 3x. I'm going to go ahead and solve for y by adding 3x over, and that's going to give me 4y is less than or equal to 3x plus 5. And then our last step to divide by 4 to get y on its own. Remember, if you divide by a negative number, you'd have to flip that inequality. So what I'm left with is y is less than or equal to 3/4 x plus 5 over 4. So this is going to be a line. The slope of this line is 3/4. The y-intercept is 5 over 4. And what this is saying is I can take the points that are less than or equal to this output. So any y value that is below or equal to this line will satisfy this inequality. So the line where you replace the inequality by an equal to represents the boundary of the region. We can actually equal the points on the line because it's got that less than or equal to symbol. So we're going to go ahead and just graph this as a solid line. If you did have a strict inequality, the line's still important to graph itself, but you can't actually equal those points. So you would just do a dotted or dashed line instead. And now, since the y values have to be less than the line or equal, we're going to shade underneath it. There's another way you can figure out what region you have to shade. You could pick a point in the xy plane, see if it satisfies the inequality. If it does, you shade that region exactly, but if it doesn't, then you just shade the opposite side. So let's go ahead and graph this line first. So I've got a y-intercept of 5 over 4, so I've split these up into fourths. My slope is 3 over 4, so we'll go up 3 over 4 to get this point here. So this point is also on the line. And now I can equal anything on the line. So we're going to draw it as a solid line. And this is the equation of our line. So I can pick any y value that's less than or equal to this line. So I'm going to go ahead and shade everything underneath it. Anything in this shaded region will work for this inequality. Now, if you don't like going through that, instead what you could do is you could pick a test point. So let's pick 0, 0. If I plug this into the inequality, we're going to get 0 is less than or equal to 0 plus 5 over 4. So this is basically like our test point in here. Since it worked, that tells me anything within this region would work. So again, I can shade everything underneath the line. If it didn't work, that would tell me I shade the opposite region and I would shade above. Okay. So let's try another one. Let's go ahead and graph y is greater than 3x squared plus 2. So that equal to without the inequality is kind of that key distinguishing shape you have to draw. So we're going to graph y equals 3x squared plus 2, which is just a parabola. But since I can't equal this, I'm going to draw it as a dotted or dashed curve. And then I'm picking y values that are greater than the 3x squared plus 2. So I'm going to go ahead and shade above the parabola. So if we look at this, this is a parabola. It's going to open upwards, and the vertex is going to be at 0, 2. So my vertex would be right here, and it's a parabola that opens up, but I cannot equal the parabola. So I'm going to go ahead and just shade it in. And then I can pick y values that are greater than the parabola. So everything inside this region would work. And again, you can pick a test point. You could try plugging in 6, or you could again pick 0, 0, because that's a really nice number. So if you weren't 100% sure what to do, plug this back into your original inequality. So you would get 0 is greater than 3 times 0 squared plus 2. And it doesn't work, so that tells you don't shade this region, but shade above it. Okay? So all we're going to do to actually solve systems of inequalities is look for a region that satisfies both of them. Like with systems of equations, you get a single solution. Now I'm going to get a region instead, because there's going to be multiple points that satisfy both of the inequalities simultaneously. So what we can do, and you could go through this a couple different ways, graph those inequalities. You can do it on the same, you can do it on a separate one. I tend to like graphing each one separately, then putting it on a single plot and graph that intersection of the two shaded regions. So let's go ahead and try a bunch of examples. Let's graph the solution set of each system of inequalities. So we're going to start with this first line, and we've got a second line, and I want to make sure I'm satisfying both of them. So what I want to do is I want to solve this for y, so I'm going to go ahead and subtract 6x, and then go ahead and divide by 3. So I want to graph this inequality. So I'm going to keep the same axis for each of these, because we're going to have to combine it by 1. And since I have a strict inequality, I'm going to graph this line as dotted. The y-intercept would be at 0, 4, and my slope is -2. So I go down 2 over 1, down 2 over 1. And then we go ahead and draw this as a dotted line. So this is y equals -2x plus 4. And this end one is going to be the full system, so I'm going to go ahead and just transfer that over to this last one as well. Goes through 0, 4, goes through 2, 0, and this is a dotted line. Now I'm going to go ahead and shade in my particular region. I want the y values that are less than this line, so anything below the line is going to work. So any point in the shaded region will satisfy my inequality. Now we'll go ahead and work with the other line. So again, I want to solve for y by subtracting the 4x. So this is going to be a line. Its y-intercept is going to be 0, -4. If you go ahead and use that slope, it's going to be down 4 over 1, or up 4 to the left 1, up 4 to the left 1. And again, it's a strict inequality, so it's going to be a dashed line. So this is y equals -4x minus 4. And likewise, I'm going to go ahead and graph this on that end result I want. And so I can shade the regions above it because I want the y values that are bigger than the line. So anything up here works. So if you did go ahead and put them on the same drawing, these are the values that will work for the second equation. And then for the other line, I could pick the values below the line. And where these two intersect is going to be my overall solution. So inside the shaded purple region, I'm going to have solutions to both inequalities. So the region inside of here is going to be our solution. Okay? So this is the process you're going to do every single time. Let's go ahead and try another one that involves a line, and it'll involve a parabola. So we've got x plus 2y is less than or equal to 4. Again, I just want to go ahead and solve this thing for y. And then we want to graph it. And I'm going to use the same graph over and over and over. So this is a line. The y-intercept is at 0, 2. My slope is -1/2, so I go down 1, right 1, down 1, right 1. And it's less than or equal to, so we can draw this as a solid line. And then I want the y values that are less than this line. So everything inside of here is going to work. Now, if I go ahead and look at my next inequality, I've got y is greater than x squared minus 1. and that's just a parabola, and it's greater than or equal to. So I can draw my parabola as a solid line. Okay? And then I want the y values that are greater than the parabola. So everything inside of here is going to work. So once again, I want to draw this on a single piece. Here is the solution to my second inequality. Then I want to go back and draw my first line, which goes through 0, 2, 4, 0, and then continues on. And the solutions to this inequality are everything below the line. So I want the intersection of these two regions, so that's going to be this piece inside the parabola here and below the line. So anything inside of here is a solution to both of these inequalities. So let's try one more, and let's try to make it even more complicated. We've got y is less than or equal to x, which is going to be a line. I've got x squared minus y squared is strictly less than 1. And then I want to go ahead and graph both of these on the same. So this is just a line, goes through 0, 0. It's our identity function. And I can equal that line because its y is less than or equal to. And then I want to pick the y values that are less than this line. And again, you can use test points if you need to. If you picked like 1, 0, that would be 0 is less than or equal to 1. So this side of the graph is good. So we're going to go ahead and transfer that over to this last piece for our overall solution. Now, if I look at x squared plus y squared is strictly less than 1, that's a circle of radius 1. X squared plus y squared equals 1. But I can't equal that boundary of the circle. So I'm going to go ahead and draw my circle, but with dashed lines. So since I want x squared plus y squared to be strictly less than 1, I'm going to pick the values that fall inside the circle. And again, you could pick a test point. If I pick 0, 0, 0 squared plus 0 squared is definitely less than 1. So the pieces inside the circle will satisfy this inequality. So we go ahead and just transfer it over to our combined graph. We shade the region inside of here, and we look for that overlap. So the overlap of these two is going to be my solution, which is this portion right here. Okay? So my best advice to you is going to be to take your time with graphing these and graph them separately. Pick test points if you're not sure based on the inequality itself, especially when it gets complicated when you have nonlinear equations like this.